So welcome everyone to the day 2 of inaugural tinyML Asia Technical Forum. I'm Sakya Dasgupta, CEO and founder of Edge Cortex, and I'll be chairing today's session. It's a great pleasure to talking to all of you from Tokyo here. It's my pleasure to introduce Professor Li JIANG of the same university, Shanghai Jiao University, as the previous speaker. He will talk to us about computing in memory with thousandfold energy efficiency, an algorithm architecture co-design approach. Li JIANG is an associate professor with the Department of CSE at the Shanghai Jiao University, and he received his bachelor's degree from the same university and an MPhil and PhD degree from the Chinese University of Hong Kong. He also serves actively on a number of international and national conferences, as well as the associate editor for the IET Computers Digital Techniques, as well as the VLSI Integration Journal. So thank you, Li JIANG, and over to you.
Okay, thank you for the kind introduction. Is my voice okay? So
yes,
today my talk is computing memory with thousand energy efficiency, and different from my colleagues in last talk. In this talk, I will put more attention to the algorithm and architecture co-design approach. So first, let me introduce outline. So first, I will introduce the trend in the AI and AI chip area, and we will propose some challenges. And then I will introduce the in-memory computing, especially the ReRAM-based in-memory computing techniques and architectures. Then I will introduce actually briefly 3 challenges for these new emerging technologies. And actually, we are in the darkness, the last darkness before the dawn. I believe in the future 3 to 5 years, these new technology and architecture will become real in the industry and the commercial world. So in each of these 3 challenges, I will briefly introduce several solutions from my research group, and then I will conclude this talk. So actually, the computing power is one of the important factors for the development of AI. But in the future, computing power will become the new bottleneck for the AI. The main reason is the computing power requirement from AI actually doubles in every 3 to 4 months. But according to Moore's law, the performance of the chips, silicon chips, only doubles in more than 2 years. And in previous years, we have a very active development in AI chip. The main benefit of the AI chip is induced from the microarchitecture innovation, like put more parallelism, put more computing resources in the chip, and reduce a lot of controls. But this kind of innovation is becoming unsustainable. And from the energy efficiency point of view, the left figure actually shows a lot of different AI chips in the power and the performance landscape, and we can clearly see there is a war here. That means if we want to provide more computing power under limited power constraint, it's very difficult for the current architecture and technologies. So the third challenge is the memory war, and the left figure actually shows the bandwidth that each arithmetic unit can obtain from the past years, and we can see that the bandwidth per operation actually decreased, and in the past decade it decreased 3 times. And the right hand side is from high silicon. In the edge and the mobile devices, the memory capacity is normally limited, and we need to put more powerful machine learning models, and it has a very large memory footprint. So we need to actually find a way to meet this gap. So from the industry, there were two approaches to meet this gap. The first one is increase the bandwidth and also the memory capacity. So one of the very important techniques being used is HBM. It is one kind of a 3D memory. So actually, my earlier career is very active in this area, and one of my earlier works is involved in the IEEE standard, and it becomes a very important hardware techniques. But in the meantime, from the software part, we can see that the models are being compressed or quantized in a smaller and smaller footprint, and we will see a lot of weight parameters is being shrunk down. So I think the new architecture and this algorithm architecture collaboration should be essential to solve this challenge. And this figure shows the AI chips involvement, the development of AI chips in the past several years. And we can see that actually Google begins the domain-specific DNN accelerator architecture, the TPU, and then after TPU, there were lots of startup companies are developing those customized AI chips. And for example, one of the type is called a reconfigurable accelerator. It can be used in FPGA, and we can optimize bit width for those edge and mobile applications. Then the current phase 3 is algorithm and hardware or architecture co-design phase. So we have a capability to influence and even train at the edge and end devices, and it can provide ultra low power. And this talk will also cover this phase 3. And in the phase 4, we think it will be scalable heterogeneous design, and a computing memory architecture can avoid the conventional Van-Neumann war problem, and we can have this this one architecture, and it can serve for all the different scenarios. So this slides actually show the principle of computing memory. So the right-hand side is the conventional way. So if we want to design a multiplier, for example, for the multiplication operation, we need thousands of transistors to do that, to form a multiplier, an adder, and a register. So if we want to carry on a 1K times 1K matrix multiplication, it almost need 1 billion transistors. But if we use memory in computing architecture, you can see the right-hand side, this figure. So each device is we call memristor or ReRAM cell, and this cell is basically a programmable resistor. So we know from the Kirchhoff's current law, the voltage times the conductance, which is also the reverse of the resistance, is equal to the current. So if we place these memristor devices in a crossbar, the current actually will be accumulated in this bit line. So if we put a vector of the input and encoded it to pulses of voltages, so each of these voltage will go in through this memristor ReRAM cells, and the resulting current will be accumulated in the bit line. So from the mathematical point of view, it's a vector in a product. So using this new technology and architecture, we can finish vector and matrix multiplication in several cycles, and the hardware cost is also extremely low. So we can do a comparison with the A100 NVIDIA chip. If we want to provide the same performance, the TOPS, the transistor we need is only like less than 2 millions, but for the NVIDIA, it have 54 billion transistors. And the power will reduce from 400 watt to 7 70 watt. So this actually show that this analog computing in computing memory architecture using new technologies, processing technologies, will provide more than 100 energy efficiency than the conventional methods. And here this is actually one of the book I written with Gardner for the Shanghai government, and it survey all kinds of memristive process technologies, and actually ReRAM shows its superior advantage in cost, power, latency, almost every aspect ratio, every aspect. And especially ReRAM can have multi-level cell, and which is very suitable for AI application, and it can support analog computing and on-chip 3D integration. So this technology is one of the it's one of the most promising process technology for memory in computing in memory architecture. So later I will introduce the first challenge. So currently for computing memory architecture, one of the challenges is the memory device density is not high enough. So there will be a huge gap between the memory capacity and the machine learning model size. So one of the technique is a DNN compression. So my colleague has introduced a lot background in this domain. So I will just briefly introduce. So the most frequently used techniques is specification, as also known as pruning, and quantization. So earlier, the AI community have lots of works. It's so algorithm optimization methods to try to compress the model size. But if we put this compressed model in the real chip, in the real hardware, we see that there is no obvious speed up. The only benefit is we have less storage and less bandwidth. The main reason is if we want to see a real speed up or performance benefit from hardware side, it needs a very high cost, like indexing, a very complex and costly hardware to control, to skipping those zeros before because zero can multiply anything is zero. So we want to skip these zeros, and it's very complex in hardware. So a new way is to make the algorithm and hardware co-design collaborate with each other. The algorithm should aware of the architecture, and the algorithm need to be changed according to the characteristic of the architecture. So this is the first example, one of our earlier work. We actually test compressed neural network on GPU, and we see that even the model is compressed more than 10 times, but the actual speed up is less than 2 times. And the main reason is, as shown in this table, the sparsity, the zeros, is randomly distributed in the weight matrix. So for the hardware, especially for those high parallel computing architecture, the architecture don't have this fine-grained scheduling capability to skip those randomly distributed zeros. So it's very difficult. And for computing memory architecture like ReRAM crossbar, it's even worse, because these compression cannot even save the storage, because the ReRAM is as shown in previous slides, the crossbar structure is tightly coupled. You cannot just remove those zeros, because each column and row need to be calculated for the matrix multiplication. So our work is try to apply a structural pruning method. That is, we will prune the whole column or the whole rows of the weight matrix, so that it will be a very compact structural weight matrix. And we can put this compact matrix in the crossbar. And from architecture, we need to change the the input fetching, because we have already promed the whole row and columns of the whole rows of the weight matrix, so we don't need the corresponding input data from the feature maps. Also, we need to make alignment from in the output, because we have already promed some of the columns. And the results show that we can achieve more than 10 times speed up, and we can save almost 10 times of crossbar devices. So this is very important, because even you can have like hundreds of compression ratio. This compression ratio is actually in terms of weights, number of weights, but not the number of crossbars. So it's very important to let the algorithm to be aware of the hardware structure. And one of the thinking is in the weight matrix can be very large, and we need to map these weight matrix into the crossbar. So this is one typical Memristive crossbar. And if we can provide a more fine-grained proning. For example, if we only need to prone the column and weight of the crossbar, this hardware, this crossbar, then we will have a better compression ratio, or we will not hurt the model accuracy. So this is the basic idea. So the first figure here shows we can actually prone the column, the crossbar column, not the column of the weight matrix. So this proning the granularity is more fine-grained. And after that, if we want to, so in the second figure, we can see that some of the crossbar is saved. We don't need to map more weights on it. But if we want to continue to prone the column rows, we can see that the weight from different channels are actually in the same line of the crossbar, and due to the hardware structure, these weights in the same bit line will be calculated together as a same channel. So this is we call it dislocation problem. So we cannot prone the row and the column in the same time in this crossbar structure. So our method is to try to solve this problem by several novel algorithms. Like we first prone the weight, the matrix column. So this is pure algorithm. There's no hardware coupling effect. After that, we map the weight matrix, the prone weight matrix into the crossbar structure, and then we can continue prone the rows, continue prone these weights in a finer granularity. That is the crossbar row. So you can see different crossbar have different number of weights. So these are the two one-up solution. We also provide a block-based proning, which can decouple the hardware from the model proning, so that we don't have this dislocation problem. And here are the results from NLP and CV models, and we can observe that we can have more than 20 times reduction on the crossbars. I want to emphasize again, this is not a compression ratio for the weights, but the compression ratio for the crossbars, which is much difficult. And the accuracy drop is very limited, less than 0.1%. And one of the algorithm is actually tested in Huawei's production line. It's quite good, can meet their requirement. And the second idea is explored in training.
We have a question from VChat coming in, and it's perhaps relevant to take it early on. The question refers to that all the DNN models that you're showcasing here, it refers to an ASIC design based on these DNN models. So ASIC is the hardware that we are talking about. Could you clarify?
Is hardware, which part is hardware?
So the question is that when we are referring to hardware in your presentation, are we referring to an ASIC design based on the DNN models?
Okay, so the hardware I mentioned here is actually a general purpose accelerator. For example, in my previous slides, it's a crossbar structure. So this is the computing in memory architecture. This is you can see this structure is very good at the matrix multiplications. And in AI application, the major computation workload is matrix multiplication. So this is the hardware I referring to.
Thank you.
Yeah. So actually, the next, we want to explore the DNN sparsity during the training phase, because it's not that easy. So for this work, actually, we are targeting on the GPUs. The basic idea is that we explore the sparsity in training based on the random dropout. This random dropout is widely used in a lot of NLP models, but normally 70% and to 30% to 70% neurons and the synapses will be dropped during each batch of training. And all the machine learning framework like TensorFlow, PyTorch, what they actually do is they will, when they drop all these neurons and the weights, they will actually do the calculation and only mask the result. That means for those dropped neurons, I will do the calculation, but I will not use the result. So this is a waste of the computing power. So we want to actually save the calculation of these dropped neurons. So this is a basic motivation. But for a lot of parallel computing architectures like GPUs, also like the computing memory crossbars, the problem is that we don't have these fine-grained scheduling capability. So we cannot precisely skip those randomly distributed zeros. So as I have explained in previous slides. So our idea is a similar one. So we propose some architecture-friendly dropout pattern, like block-wise or row-based or column-based. That means we would, every time we drop the weights, we would drop a block of weights instead of a single weights. So this is the basic idea. But the problem is this will hurt the randomness of the dropout. So our solution is to develop a dropout pattern search algorithm. So we will search different kind of patterns so that eventually each weights or each neuron is dropped purely random. So we have provide a mathematical bound for this method. We can save almost half of the training time. We actually have an experiments on a language model, NLP language model. Normally the training this model requires 1 week, and we can accelerate it, and we can finish the training in 3 days. So there is actually a very active research for training acceleration in like low bit width digital domain and analog domain. And we also will pursue, we will continue study on this direction. So in the short summary for the pruning, there were non-structural pruning, which the zeros are actually randomly distributed in the weight matrix. There are also a lot of structural pruning methods like vector-wise, row-wise, column-wise, channel-wise. The problem is it will reduce the randomness of these zeros, and it will hurt the accuracy. So NVIDIA in their A100 GPU chip, they provide a row-based irregular pruning method. So every channel, every row in the weight matrix will be pruned by half. So this is a fixed number. The reason they want to prune them by half is because after pruning, they can have a dense matrix. But here you can see that they don't have a very clear structure here. Actually in each row, the weights can be prone randomly. So this is very good for preserve the accuracy of the model. And we also provide a column balanced irregular Pruning method, especially in Van-Neumann domain. And this method is particularly useful for FPGA based hardware accelerators. And after introducing the Pruning methods, now we let me introduce several of my works in quantization. So actually, Professor Kai Yu has introduced a lot of quantization methods like weight clustering, sharing. They try to reduce the number of values of weights can represent, but it need costly indexing. So this is the hardware cost, which is not presented in the previous talk. There are also other ways like fixed quantization, binarization. The drawback is it may hurt the accuracy of the model. There are also adaptive quantization methods. So here, actually, we find a dilemma for this kind of quantization methods. That is, you cannot have the hardware cost reduction and the high precision in the meantime. It's very difficult to optimize both of these targets. And we have a work in this year's ISCA. The basic idea is to explore more sparsity from the input. And we can see that from the image, actually, there was some region which are meaningful for the final production prediction, but others like background is not that meaningful. So we find that different pixels actually have different impact on the accuracies. We can have some very sensitive values, but for example, the large values will have greater impact on the accuracy. And those sensitive input actually will aggregate it in the space, and we will define them as sensitive regions. So our basic idea is try to use a high precision model for sensitive regions, but for using a low precision model for the insensitive regions. And this is the algorithm. The algorithm is very simple. We will have a very simple, lightweight predictor to look the input feature map ahead of the heavy model. So it will give a mask telling us which region is sensitive and which region is not sensitive. So different regions will be sent to different part of the model. So for the lightweight model, the low precision model, we will use a 4-bit quantized convolution tensors. But for the high precision, we will use 8-bit quantized convolution tensors. So this algorithm will be deployed in the chip as a predictor. So this is the architecture of this method. Actually, the architecture is more sophisticated because the input will be the input will be actually quantized in different way, in different bits. Some of it is in 4 bits, some others are 8 bits. So we need to rearrange the data layout in the line buffer. Then the line buffer is sent into the PEs, the processing element. That processing element should be a multi-precision application. It can be customized ASIC design. It can also be a computing in memory architecture like ReRAM crossbar, as long as you can provide different precisions. And also we need to synchronize the pipeline, because if you use a ASIC design, the PE will become the speed of the PE will become variable. It's not a fixed speed. So we need to tune the pipeline to synchronize the result. So this is the main idea of this work. At last, we explore the bit level sparsity for energy efficiency. So the main observation is in the memories, in a lot of in emerging memories like ReRAM, we find that reading bit 1 and reading bit 0 will incur dramatically different energy consumption. And this is mainly because of the peripheral circuits like analog digital converters. And the key idea is to search the binary code of the way to try to balance 0 and 1. Yes.
I would suggest that we start summarizing since we are running out of time, perhaps another couple of more minutes. So if you can start summarizing, it would be great.
Okay, great. Yeah, so the basic idea is to tune the weight of network to get a much higher energy efficiency. So this is the outline, and for the second part, actually, I will skip this one because it's mainly in hardware, and I want to highlight that we propose a retraining method to learn the defects among these emerging memories, and it is well accepted in the academia. And the last one is AI-based approximate for adaptivity, because for the computing memory architecture, it only suitable for memory for the matrix multiplication, but a lot of different algorithm is not weight matrix application multiplication. So this is our main idea is to use the neural network to approximate those different kind of algorithms. It can give us higher parallelism and it can give us better adaptivity. So here I will skip several of our works. So I want to, though this is the chip we tape out, we also develop a tiny AI compiler to support the sparsity so that the model can be trained in the edge or end device with limited resource. We have developed this tool based on TVM and migrate it to memristor. So I want to use David Patterson's. I want to quote David Patterson to conclude my talk, because the cross-layer co-design, like algorithm architecture, is very challenged because we need to consider a lot of different knowledge challenges and problems from different levels, like device level, architecture level, algorithm level, and it is a very challenge. And to conclude my talk, we have presented several of the Pruning and Quantization algorithms collaborated with the architecture design. So with this method, we can compress a large learning model into a tiny DNN models and deploy it into computing memory chips. We also provide some approximation method to approximate those near sensor algorithms, domain-specific algorithm like signal processing, image processing into a tiny DNN. And these tiny DNN can be deployed and executed by the same chip, and we will optimize the accuracy, energy, performance, also the cost of the hardware. And we also provide a compiler technique to put all these things together. Actually, we need a very successful tool chain to make this software and hardware co-design successful. And that is my talk. Thank to my sponsors and collaborators. Thank you.
Thanks a lot, Professor Li, for that very interesting talk. Unfortunately, we have run out of time for questions. So I will recommend, if there are questions, people can submit this on the VChat group, or you can, submit your questions here or on Bilibili, and we will relay it to Professor Li. So if, Professor Li, you could take those questions offline, that would be great. Thanks a lot once again for your very interesting talk on a hardware-software co-design aspect for tinyML. I would like to thank our sponsors once again, without whom the tinyML Asia Forum would not be possible and be available for free of charge. Starting with ARM, our premier sponsor, the software and hardware foundation for tinyML. Edge Cortex, their dynamic neural accelerator brings near cloud performance to the edge devices. Finally, SynSense, SynSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Thanks a lot once again to all our sponsors. I would also like to thank our partners, conference partner SHAI, as well as all our media partners. So that brings us to the end of today's session, and I look forward to seeing all of you once again tomorrow for the day 3 of tinyML Asia. Thank you, everyone. Thanks all our speakers and all our sponsors once again. Thank you.